Hey everyone, and welcome to The Explainer. Today, we're going on a seriously incredible journey. I know you already know the basic parts of your rig, but today we're going to trace the exact millisecond by millisecond journey of data, from a totally cold boot all the way to a global network request. We're literally stripping away the case to look at the fascinating mechanics of how efficiently these complex processes happen. It's going to be awesome. Okay, so here's our blueprint for today. We'll start with waking up the system, then dive into the brain and memory, check out graphics and heat control, trace our input and output loops, look at connecting to the internet, and finally bring it all together into the complete system. Let's jump right into section 1, waking up the system, starting with that exact physical trigger, the power button. So, looking at our setup here, we've got the usual hardware suspects, right? The motherboard, CPU, RAM, storage drives, GPU, power supply, and of course, the cooling system. Right now, it's just a bunch of dormant silicone and metal. But in a fraction of a second, that state changes completely.
The chronological flow kicks off instantly. You press power and boom, electricity floods from the PSU, surging straight into the motherboard. This immediately triggers the BIOS handoff, which then loads the operating system. It all happens in mere seconds. Honestly, it's an absolute marvel of microsecond engineering.
Now, you definitely know the BIOS or UEFI as that system you boot into to tweak your core settings. But structurally, it acts as the strict project manager of this whole ecosystem. It runs all those power-on self-test checks to ensure hardware stability before formally passing the baton over to your OS. Right, moving on to section 2, the brain and memory, which is where the core processing loop really gets going. Those initial electrical sparks we just talked about, they immediately become highly structured data streams. Across the microscopic traces of the motherboard, data is shuttled via high-speed buses directly to the processor. We're talking highly organized information moving at just incredible speeds. It's like a digital superhighway in there. Right at the center of all this is the CPU, continuously running its rapid-fire cycle. It fetches instructions, decodes the required mathematical logic, and executes them. It's this beautifully simple, elegant three-step loop. But here's the crazy part. It's happening billions of times per second across multiple cores, all concurrently. To keep that cycle fed, the CPU relies on a really strict memory hierarchy. It pulls those permanent, heavy files from your long-term SSD. But because of latency constraints, it stages the active data it needs right now in the RAM. Basically, the CPU needs non-volatile storage for safety for sure, but it relies heavily on the sheer bandwidth and ultra-low latency of the RAM so it doesn't bottleneck its execute cycle. Think of it like moving from a slow, deep storage filing cabinet to your active desktop workspace. Okay, let's pivot to section 3, graphics and heat control, focusing on visual output and keeping the system stable. Enter the GPU. So, while the CPU handles sequential logic, the GPU is your parallel processing powerhouse. It is custom designed to calculate thousands of shading effects, pixels, and vectors all at the exact same time, translating massive data pipelines into those fluid, high-resolution frames we all love. But, and this is a big but, this intense fetch-decode cycle and all that massive parallel rendering, they generate a severe thermal load. The cooling system, whether you're running air or liquid, is actively mitigating this thermal design power, or TDP. Without rapid thermal displacement, these chips would literally hit their thermal junction and self-destruct in a matter of minutes. No joke. Let's shift over to the user experience in section 4, input and output loops. Interaction is essentially a continuous physical loop. When you actuate a key or move your mouse, you're sending hardware interrupts directly to the CPU. It processes these electrical signals and updates the display output so ridiculously fast that system latency essentially vanishes. It creates this totally seamless illusion of physical control.
All right, moving to section 5, connecting to the internet. The crucial point here is how this isolated desktop reaches out to the rest of the globe.
Our local ecosystem is really just the starting point. We use the physical layer, either an Ethernet connection or Wi-Fi, to push data to our local routers. From there, the router acts as the gateway, establishing protocols to communicate with external servers that are often housed in data centers thousands of miles away. And that global conversation relies entirely on packet switching. You see, your data doesn't travel as one giant, monolithic block. It's fragmented into tiny, dynamic packets. So every single web page you load is actually thousands of these packets dynamically routing through optimal network nodes just to be reassembled instantly on your screen. It's wild to think about.
Finally, we reach section 6, the complete system. Let's bring it all together and summarize the complete anatomy of our machine.
When fully integrated, what we're looking at is perfect hardware synergy. From the communication backbone of the motherboard, to the distinct memory hierarchies, the parallel graphic rendering, and of course, that absolutely critical thermal mitigation. Every single component plays a distinct, beautifully synchronized role in executing your commands flawlessly. So, I want to leave you with this thought. Next time you sit down at your desk and hit that power button to boot up, will you picture those glowing digital data streams flowing right under your fingertips? It truly is an invisible kinetic ballet happening inside your everyday devices, working tirelessly to connect you to your work, your art, and the rest of the world.
It really does put into perspective just how masterful the engineering behind these tools actually is, doesn't it? Well, thank you so much for joining me on this deep dive. Be sure to subscribe to MindSpark for more amazing How It Works explainers just like this one.